trans isomer is more stable than cis isomer. Cis is less stable, trans is more stable. Notice, you can burn paper, you can burn wood, you can burn cotton. Whenever you are burning these, some heat energy is released that is known as heat of combustion. But can you burn water? Can you burn carbon dioxide? Is it possible to burn water or CO2, sir?
No.
The heat of combustion of water is zero. The heat of combustion of CO2 is zero because they cannot be burnt. So, more is the amount of heat of combustion, more instabilities. If a compound is already stable, it will not be able to be burnt. You understand? So, the heat of combustion is a measurement for stability of a compound. More is the heat of combustion, less is the stability. Less is the heat of combustion, more is the stability. If heat of combustion is zero, that is very, very, very stable. Are we very clean about it? Now, if a compound has H, double bond, H, and Cl, Br. Now, in how many ways this compound can exist, sir? It has two double bonds. If both hydrogens are on the same side, it is cis. If both are on opposite sides, it is trans. If these, I would say, if both hydrogens are on the same side, again it is cis. If they are on opposite side, it is trans. Agreed or not? When this is cis, it can be cis or it can be trans. When this is trans, it can be cis or it can be trans. In Sir, in this compound, if this hydrogen are on the opposite side, it is called trans. If this hydrogen are on the same side, it is called cis. Similarly, if this hydrogen are on the same side, it is cis. If they are on opposite side, it can be trans. Agreed or not? Agreed?
Yes.
Hello?
Yes.
Now,
Sir, agreed.
when this is trans, it can be trans. When this is cis, it can be cis or it can be trans. So, in how many compounds can exist? 4 ways. Yes or no? Yes?
Yes.
When the ends are different, if a compound has n double bonds, number of geometrical isomers is 2 to the power n. I repeat, when the ends are different, When there are n double bonds, I call them as stereogenic centers because they are the centers which cause stereoisomers. If there are n stereogenic centers, there can be 2 to the power n stereoisomers
Sir, I not
or
understand this point, sir. 2 power
geometric
n.
isomers. What can I do? What can I do? When this hydrogen are on the same side, it is called cis. When they are on opposite sides, it is called trans. When these hydrogen are on the same side, it is cis. When they are on opposite side, called trans. Now this molecule has a 2 double bonds. So there can be situation like this is cis, this is also cis, or this is cis, that is trans. Or it can be trans and that is cis, or it is trans, this is also trans. So in how many ways this molecule can exist? In how many ways?
4 ways, sir.
4.
Cis cis,
Four,
cis
sir.
trans, trans cis, trans trans, 4 ways. It has 2 stereogenic centers and it exists in 4 different ways. So I am saying generally, if ends are different, if a compound has n double bonds or stereogenic centers, it has 2 to the power n geometric isomers or stereoisomers. Any difficulties there?
No.
Sir, ends
Suppose
are
you are
different means.
considering a, now you can consider a molecule like this CLB or CLI, CLH, whatever. Double bond, single bond, double bond, single bond, double bond. Now, how many isomers it can have?
8.
If you want to work, you work out like this. Cis trans, cis trans, cis trans, cis trans. When this is cis, it can be cis, it can be cis. When this is cis, it can be trans, it can be cis. When this is cis, it is trans and it can be trans. Like that, you have to work out. If you work out, how many you will get?
8. 8.
Hello. Answer is 2 to the power 3, 8. Which is easier, applying formula or working out like this?
Applying formula.
Formula. Sir, ends are
So I
different
gave a
means.
formula. Here you have Cl, here you have H, here you have Cl, here you have Br. In the end, the atoms are not same. If ends are similar, then for example, if both are hydrogens, then the number of stereoisomers will decrease, right? Because the ends cannot show cis trans isomerism, right or not? Both are hydrogens,
Yes, sir.
then whether the hydrogen is up or down makes no difference. Then the stereoisomers are only due to central double bonds, then the formula changes. So I gave a very useful formula when the ends are different. If there are n stereogenic centers, a stereogenic center can be a double bond or a ring or a chiral carbon. What is a chiral carbon? I will be talking to you later on. Now, anyway, if there are n stereogenic centers, if the ends are different, it can have 2 to the power n stereoisomers. Have you understood? Hello?
Yes.
Hello?
Yes, sir.
Now this is communication, not noise. Always you should see whether it is communication or noise. Thank you very much. Now we are looking at next idea. Now geometrical isomers, I already said that trans is more stable, cis is less stable. Heat of combustion of trans is less, heat of combustion of cis is more. Cis cannot itself be converted into trans. If you want to convert, you have to break the double bond, which requires 650 kilojoules energy. And geometrical isomers arise when there is a restricted rotation. If there is rotation, you get conformers. If there is no rotation, you get geometric isomers. Now we are looking at next idea. Ordinary light coming from sun has ability to vibrate in how many directions?
All directions.
Infinite directions. All.
When the light is passed through a prism made with CaCO3 nicole prism, the outcoming light can vibrate in only one direction, then that is called plane polarized light. This plane polarized light has a great property. When it is passed through some substances, you take a certain substance in a test tube and allow the plane polarized light to pass through. When this is passing through some materials, either it is rotated clockwise or it is rotated anti-clockwise. Materials which can rotate the plane polarized light are called as optically active compounds. To be optically active, one rule is a compound should have carbon locked to 4 different groups. A carbon which is bound to all 4 different groups is called asymmetric carbon or chiral carbon. If a chiral means hand, your left hand is mirror image of right hand. You can see yourself. If you are looking at your left hand in mirror, it looks like your right hand. Yes or no?
Yes, sir.
Yes.
Anything that looks somewhat different in mirror is said to be optically active. The object and image, they convert left to right, right to left. Then that is said to be optically active. Your hand is optically active because really you cannot cut your hand into 2 equal parts. Can you?
No.
In any way, look at your hand. Think, can you cut it into 2 equal parts? Can you divide into 2 equal parts? Yes or no?
No.
No, sir.
Anything that cannot be divided into 2 equal parts by doing any cutting, then that is said to be asymmetric. Asymmetric molecules are optically active. They look differently in mirror. You look at English alphabet A. How it looks in mirror, capital A. Is it different?
Same.
If you look at B, is it looking same?
No, different.
So you
But
can see that in English alphabet, some letters are optically active. Is C optically active?
No, sir.
Is C is same in mirror image and in the script, or is it different?
It is different.
different.
Definitely it is different. You
Different.
cannot cut C into 2 equal parts. You try to cut C into equal parts. One part is coming down, one part is going up. You can't cut C into 2 equal parts. If you want to cut vertically, one piece is like horizontal, one piece is like small pieces. I'm sorry, C is not symmetric. C looks differently in mirror. What about X?
Same, sir.
Same.
X is
Same, sir. Not
X is
optical. Symmetric, sir. Excess symmetric.
X is a
Symmetric.
chiral. X is echiral. Echiral means not optically active. A is echiral, not optically active. B is chiral, optically active. What about donkey D?
Not chiral.
Different, sir. Optical.
It is
Optical
chiral.
nahi. Optically active, dirty rogue. It is optically active, okay?
It is chiral.
Chiral, sweet boy. Right. What about E? E for elephant.
Optically active.
Very good, sir. So now you
Chiral.
can see, a chiral is not active, chiral is active. What about O?
Optically
Chiral.
inactive.
Optically active. Chiral.
Optically inactive or a chiral, not like hand. Chirality means hand. A chiro practitioner is one who looks at your hand and tells your future. You know, there are some people who can read the hands. Do you know?
Fraud, yes, sir.
Of course, it may be fraud or it may be nonsense. But there are people who do that. Do you agree or not?
Yes, sir.
Yes.
I'm not declaring that it is right, that is a science or not science. I don't know. But there are people who are practicing hands, looking at hands. So they are called chiropractitioners. Anyway, chirality means related to hand. Okay. Now, a chirality is due to a symmetry. Molecules which don't have symmetry, molecule which cannot be cut into two equal parts, molecule which has a object image relationship possibility, molecule that can rotate plane polarized light either in clockwise direction, its mirror image which rotates plane polarized light in anti-clockwise direction. They are all said to be optically active compounds. To be optically active, molecule should not have, molecule should be chiral. To be optically active, molecule should be chiral. And notice, if any compound has a asymmetric carbon, a carbon locked to 4 different groups, definitely it is optically active. Now, look at this molecule, sir. Does it have any chiral carbons? If yes, how many? This carbon is locked to 3 hydrogens. To be chiral carbon, carbon must be locked to 4 different groups. These are not different groups. All are same hydrogens. Therefore, this carbon is not chiral. This carbon is locked to 2 identical hydrogens. So it is not chiral. What about that? Is it chiral?
No.
Hello?
No.
No. What about that? Is it chiral?
No.
It is
No.
locked to Cl. It
It
is
has
locked to
two.
Br. It has a ethyl group this side, another ethyl group this side. Is it ethyl or methyl? 1, 2, 3. It is 2. One side 2 carbon chain, one side 3 carbon chain, one side Cl, one
Chiral.
side Br. It is chiral. This carbon is not chiral. This carbon is not chiral. So this compound has how many chiral carbons?
1.
1.
This has how many chiral carbons?
0.
0.
Zero, sir. Zero.
This has how many chiral carbons?
1.
This has two
Two.
hydrogens.
Two.
It is not chiral. Not chiral. Not chiral. Not chiral. They don't write hydrogens, you should
Sir.
think. It has one hydrogen, a carbon chain like this, a carbon chain like this. Definitely this carbon is chiral, yes or no?
Chiral, sir.
Yes.
Yes, sir.
What about this carbon? What about this carbon?
It's chiral.
Chiral, sir. Chiral.
What about
Chiral.
this carbon?
Chiral.
Chiral, sir.
Chiral.
This carbon is a chiral, this carbon is
Not.
a chiral. A chiral. So how many chiral carbons?
Three.
One.
3.
This is the IIT mains question. Let us look at the IIT advanced question. Oh, yeah. How many chiral carbons it has? Yes, sir. How many chiral centers are present in cholesterol, which is supposed to cause heart attacks? Have you noticed it is alcohol? Have you noticed that it has 4 rings? Tetracyclic compound. Oh. Sir, how many chiral carbons are there? Can you work out or should I do? But Takuru and Takuru Lakutukulodam.
Six, sir.
Eight.
Sir?
8.
6.
Wow, you
8,
might
sir.
have,
8.
somebody has Googled it.
10,
But
sir.
dirty rocks, I know somebody has Googled it. Come on.
8,
No,
sir.
sir. No, 8, sir.
Yeah,
10, sir.
those who are saying 8, are you saying 8 without consulting Google? Please tell me.
No, sir.
Honestly.
Yes, sir. Honestly
You have
saying.
not
Not.
Answer is 8. Now I want to show you which carbons are chiral. No, 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 no. Actually, morning I have shown. Oh, it has come.
Label the 8 chiral centers in cholesterol. How many stereoisomers are possible for a molecule with this many chiral centers? Well, first we need to figure out what each points of differences, and therefore this is a
Now they have pointed out all chiral carbons with red
carbon
color.
on
Can
the
you see?
left, on the right,
Can you
and on the
see?
bottom.
This is the way to
On
work
the
out.
left, the carbon is definitely
When
different
the
from the
carbon
right
is having a
because
double
it's
bond,
connected to
it is
hydrogens.
flat.
It's not connected to
Any
single
sp2
carbons.
hybridized carbon with a double bond
Here,
cannot be chiral.
on the
A
bottom,
flat
this carbon is
molecule cannot be
connected to 2
chiral.
carbons,
Three-dimensional molecules where the
while on the
carbon locked
right,
to
the
4
carbon is
different
only
groups is
connected to
chiral,
1 carbon.
not the carbon that has double bond.
Therefore, this is
Never the
also
carbon that has
a
double bond.
chiral
Are we very
center.
clear?
Okay,
Yes, sir.
Please
excellent.
notice, if a compound has n chiral
Okay,
Yes,
centers,
sir.
we have
total
1, 2,
number of
3, 4.
stereoisomers is given by formula 2 to the power n.
One.
Are we very clear?
And let's go ahead
Yes.
and
So
look at
this
this carbon.
cholesterol can have 2 to the power
I'm
8
not sure if I did
isomers,
it or not yet. Maybe I have
large
erased
number of
it already,
isomers,
but
right?
let's go ahead and do it
Are
again.
we
So
very
we have
clear?
a hydrogen.
Yes.
Let me go ahead and erase the
Now we
dots
back to
first.
our
So
discussion.
Sir, cholesterol
Sir,
again, sir.
you can browse, Now we have very less time. Now I can't go back. I have a point to say. Sir, there is a gentleman called Louis Pasteur. Have you heard his name?
Yes, sir, we have heard about it.
Have you heard him? Yeah,
Yes, sir.
he is the man responsible for pasteurization. The milk is really pasteurized so that at 67 degrees centigrade it is kept for a while, half an hour. All bacteria are killed and then it is sealed. That's the way the milk is really stored and transported. A great man who discovered pasteurization, he identified a compound called tartaric acid. So this is tartaric acid. Carbohydrate. So it has total 4 carbons. 1, 2, 3, 4. Can you name this compound, sir? Can you name this compound? Can you name this compound?
2,3
So 2,3
dihydrogen.
dihydroxy butane 1,4 dioic acid.
Dioic acid.
For oic acid, no need to say position because it is always terminus. It is butane dioic acid only. This tartaric acid is there in your sambar. Do you like to eat sambar, sir?
Yes, sir, it is
Yes,
in
sir.
tamarind.
Yeah, it is there in tamarind. So I can write the tartaric acid in 3 different ways. And of course, I am differing the location of OH groups. I kept one OH group right side, one left side. I wrote both OH groups right side. I wrote both OH groups left side. Will it really matter? That's what I want to examine. Actually, if you look at the crystals of the tartaric acid, it is available in 3 different crystal forms. First set of crystals, they look like object and image. This is the object, this is the image. A pair of crystals look like object and image. Third variety looks different. And the A type of the tartaric acid is optically inactive. It is not rotating plane polarized light. B and C, if B rotates clockwise and C rotates anti-clockwise. Notice, does it have any chiral carbons? Is it chiral carbon? Is it chiral carbon, sir?
No, because double
The
bond is
COOH carbon cannot be chiral because it has a double bond.
Double
So,
bond.
is it chiral, sir?
No, sir.
yes, sir.
Dirty rogues,
Yes.
you are not seeing properly. This carbon is locked to COOH, OH, H, one side CHOH, COOH.
Yes, sir.
This carbon is definitely locked to 4 different groups. Can't you see?
Yes, sir.
Can you see or not?
Yes, sir.
So it is chiral center. What about this carbon?
It
Chiral.
is on high.
Yes, sir, chiral.
Yes,
It is
sir.
also
Chiral
chiral.
center, sir.
So they have 2 chiral carbons. How many chiral carbons?
2.
How many
Two.
chiral carbons?
2.
If there are 2
2.
chiral carbons, Now you would like to look at the molecule, whether you can cut the molecule into two equal parts. If you can cut the molecule into two equal parts through any line, then this will be optically inactive. The molecule is said to have a plane of symmetry, plane where you can cut into two equal parts. If it has a plane of symmetry, it is optically inactive. This molecule does not have a plane of symmetry. It cannot be cut into two equal parts. So it is optically active, available in D and L forms. Though this has two chiral carbons, because it has a plane of symmetry, it is optically inactive. One part of the molecule plane polarized light in the clockwise direction, the other part rotated in anti-clockwise direction. So one portion is cancelled by other part. This is called internal compensation, because of which the molecule is optically inactive. It is called mesotartaric acid. Notice tartaric acid can be D-tartaric acid, L-tartaric acid, and mesotartaric acid. Though it has two chiral carbons, it is not showing 2 to the power 2 4 isomers. It is existing only as 3 optical isomers because it has a plane of symmetry. So all the molecules which have plane of symmetry, which can be cut into two equal parts, even though they have n chiral carbons, they don't show 2 to the power n optical isomers. They show 2 to the power n minus 1 optical isomers. 2 to the power n minus 1 optical isomers. 2 to the power n by 2 minus 1 mesoisomers. Because n is equal to 2, 2 to the power 2 by 2 minus 1 will be 2 to the power 0. It will show 1 mesoisomer. Therefore, there is a formula to calculate the number of optical isomers. If the molecule does not have any plane of symmetry, if it cannot be cut into two equal parts through any plane, then it has 2 to the power n optical isomers. If it can be cut into two equal parts through any plane, then the number of optical isomers will be 2 to the power n minus 1, and the number of mesoisomers which cannot be optically active is 2 to the power n by 2 minus 1. Are we very clear, sir?
No, sir, can you
These are
explain this third one again?
If a compound has a plane of symmetry, then the number of optically active forms is 2 to the power n minus 1. The number of mesoforms is 2 to the power n by 2 minus 1, where n is the number of chiral carbons. Carbons locked to 4 different groups. If a compound has only one chiral carbon, definitely it is optically active. If a compound has two chiral carbons, it may be optically active, it may be optically inactive. It is optically inactive provided if it has any plane of symmetry. Tartaric acid, it possibly can have a plane of symmetry. Therefore, its number of optical isomers is 2 to the power n minus 1, 2 to the power 2 minus 1 is 2. And the number of mesoisomers is 2 to the power 2 by 2 minus 1, 2 to the power 0, that is equal to 1. So this is an idea on optical isomerism, which I am not able to progress further because it is not there in 11th class portion. But I wanted to give you an idea. There are compounds which are optically active. Instrument which is used to measure optical activity is called polarimeter. The light used to detect the optical activity is called plane polarized light. So many medicinal compounds which we take are optically active. If a compound is a medicine, its mirror image can be a poison. So the optical purity of compounds often is very, very important. And cholesterol is a molecule that has 8 chiral centers. If a compound is having n chiral centers with no plane of symmetry, number of optical isomers is 2 to the power n. If it has a plane of symmetry,